Welcome. This is Nathan Weezy from Marquette University, and this is Digital Control Power Electronics. In this section, we're going to talk about the digital control of voltage mode control for a BuckBoost converter. And what we are actually going to do is work on our work off of our previous section and convert the continuous time controller to a digital controller. So a lot of the work from the previous section has been laid down and a continuous time controller has been designed. So let's kind of briefly go over what happened here. We have here in this MATLAB script our BuckBoost parameters for the application or design that we are considering. In lines 1 through 13, these essentially define all our parameters, ESR, output power, etc. Then we have the plant transfer function. In these lines here, they define it, and you can calculate the Bode plot and find the poles and zeros and all that good stuff on the plant. In lines 30 through 33, essentially what we have here is the controller design parameters. And essentially what we can do is select our bandwidth, which is 30, and we can select our phase margin, and our calculation will be automated with this script for the purposes of finding the zero pole and controller gain based upon these parameters. And this right here, these lines 35 through 46 is the controller design. And essentially when these are done running, you'll get the controller design. By line 36, you'll have the pole location, the zero location, and we'll also have the integrator gain. And that's kind of where we ended up last section, was this continuous time controller with a phase margin of about 60 degrees and a bandwidth of 1 kilohertz. Now what we're going to do is take a look at this and convert these to the digital domain. And the way we're going to do this is use our approximations in the digital domain. So we're going to do this twice. So once we're going to try at 10 kilohertz, and another attempt we'll try at 50 kilohertz. And what this is we're creating two different digital controllers at two different sample rates. So one's faster than the other, and just kind of see the effect of the sampling rate of the controller versus the switching frequency of the actual BuckBoost converter. In our case, we're switching at 200 kilohertz. So this is going to be, for instance, 20 times slower, and this one here will be about 4 times slower, the 50 kilohertz. And for each frequency of the controller, the sampling time, we're going to have 3 different controllers that we're going to consider. Here we'll have backwards Euler, and then we'll also do zero order hole and Tustin, and the same goes for 50 kilohertz. Backwards Euler, we'll just call it BE. We'll have zero order hold and Tustin. So we'll have a bunch of different digital controllers to consider. And what I'd like to say is you can simply copy and paste this into MATLAB and run it and look at what the output of this controller is. So the first controller we're going to consider here is a 10 kilohertz. So this popped out of our MATLAB script, and it's backwards Euler. And the first thing you can notice is that the output voltage is wildly oscillating. There's going to be a transient from 10% of full load to 100% of full load, and that's going to happen at time equal to 0.1. And you can see from this plot that it never settles down. In fact, you can also see the discrete sampling time of the output of our duty cycle here. And so essentially the controller is having a hard time tracking the output voltage due to this transient, because essentially converting this to a controller at 10 kilohertz with backwards Euler has made this system unstable. We've gotten essentially the poles of our system very close to the unit circle. So that's not good. This is not a good design, but just to show you that we can't just blindly, arbitrarily pick a sampling frequency and apply backwards Euler. Now here's the same simulation, except for we're at 10 kilohertz and we're using Tustin approximation. And you can see that in this case, the output voltage does decrease, but it comes back and it ends up settling. And so this one, although not perfectly damped by any means, is stable. It will stabilize, so it goes like this, but it rings a little bit longer. So there's not a lot of damping here. Essentially, we had 60 degrees of phase margin. We had a decent amount of damping in the continuous time. Here, it's just not as good, simply because of the quantization and how far we have 10 kilohertz away from the switching frequency 200 kilohertz while simultaneously trying to track a signal at 1 kilohertz. So this is an okay response, but let's go ahead and bump this up in terms of the controller frequency, sampling rate of that. So here's 50 kilohertz, and this is backwards Euler. And what you can notice now is that the output voltage goes down and comes back up, but then it settles. This is looking very close to what we had for the continuous time response. We don't have that second ring like you can see clearly here in the 10 kilohertz Tustin. You can see it go down again and ring out. It means we're having less phase or less damping. Here we have pretty good damping. Okay, and again, this here is we're in voltage mode, so this is our duty cycle. You can see the discrete steps are now at 50 kilohertz for the duty cycle that we're applying. You can see our current goes up, overshoots a little, and then locks in. So this is looking like a pretty decent response. And again, this is 10% load up to 100% load. So this is, a pretty drastic case in terms of load stepping. So you'd expect lower load steps to essentially have better response, meaning that your voltage, for instance, won't go down as much and won't ring. It'll be more damped. So when we test these, we generally try to test very large steps, because anything less than the large step is going to be better in terms of response time and under voltage or over voltage shoot and under voltage shoot. So kind of lastly here, we have our response for the Tustin at 50 kilohertz. And you can see our controller design here. You can see this one looks even better than the other one. We go down, we come up, we barely overshoot, and then we lock right on in terms of the output voltage. You can see the current overshoots a little bit, then locks into the full load current, which is fantastic. It's exactly what we expect. And this here, U is our duty cycle. It goes up, kind of undershoots, and comes down and settles back down, which is what we expect here. So this is looking really good in terms of our duty cycle here. And so this controller, you could go with 50 kilohertz here. This would work fine. You could also try looking at 200 kilohertz. Some issues would arise there too once you're essentially trying to establish a bandwidth or a filter at 1 kilohertz while you're sampling at 200 times higher. The ratio between the bandwidth and the frequency at which you're trying to sample at is quite high. Sometimes you run into accumulation problems there because you're accumulating over a lot of samples. You have to have a large accumulation size or bit size. So, for instance, 32 bits versus 16 bits. Okay, so this will conclude the digital control design for a voltage mode controller for a BuckBoost converter. Thank you.